It wasn't built to chase. It was built to end you. With jaws that opened wider than a lion's and fangs longer than your hand, the saber-toothed Smilodon wasn't just another predator. It was a prehistoric executioner. But how exactly did this silent killer strike so fast? And why did its reign suddenly end? Smilodon belonged to a special branch of cats called Machairodontinae. These saber-toothed cats split from other big cats around 20 million years ago. They are not in the same subfamily as lions or tigers. Over time, they grew longer canines and stronger neck muscles. Those changes let them open their jaws very wide. Though many people still call Smilodon the saber-toothed tiger, it was its own group of cats. Paleontologists have found hundreds of thousands of saber-tooth fossils, mostly in tar pits and cave sites. Today, scientists recognize 3 Smilodon species. The earliest, Smilodon gracilis, weighed about 60 to 100 kilos and lived from 2.5 million to 500,000 years ago. Smilodon fatalis came next, with a weight of about 160 to 280 kilos, a shoulder height near 1 meter, and a run from 1.6 million to 10,000 years ago. Finally, Smilodon populator was the largest, reaching up to 400 kilos and living mostly in South America. Smilodon's story began around 2.5 million years ago in North America. Its ancestor, Megantereon, crossed from Eurasia earlier in the Pliocene. As climates shifted, S. gracilis spread south into Central and then South America. Later, S. fatalis replaced S. gracilis in much of North America. Around 1 million years ago, S. populator evolved in South America from the gracilis stock. These moves track the rise of grasslands and the link between the two continents. When the Isthmus of Panama rose 1.8 million years ago, it let North and South animals mix in a flood of new rivals and prey. Saber-tooth style did not start with Smilodon. Ancient relatives like the Nimravidi in the late Eocene and the Barbariphelids in the Miocene evolved long canines first. Marsupial predators called thylacosmelids in South America also grew saber teeth. Then came the true saber-tooth cats, Machairodontinae, to which Smilodon belongs. Each group raced toward the same design by chance, not by sharing a close link. This repeated rise of saber fangs is a clear case of convergent evolution. The upper canines of Smilodon were its most famous feature. In the largest species, S. populator, those teeth reached almost 28 centimeters long. The teeth were flat side to side with fine serrations on the front and back edges. This shape helped the cat slice through flesh, but it also made the canines fragile. Too much twist or a hard hit against bone could crack them. To use these fangs, Smilodon had to open its jaws very wide, up to 110 degrees, compared to a lion's 65 degrees. The jaw hinge sat low, and the skull formed deep grooves where the neck and jaw muscles tied in. A tall sagittal crest on top of the skull held strong temporalis muscles. Wide zygomatic arches, cheekbones, anchored massive masseter muscles. Together, these let the cat power its bite and hold a big gape without tearing its tissues. Yet, Smilodon's bite force was lower than that of modern big cats. Studies show its bite was only about a third as strong as a lion's. That did not matter because Smilodon did not crush bone or lock down prey with sheer jaw strength. Instead, it used an aimed stab and slice approach. The thin canines made clean cuts but risked breakage if used clumsily. Several skull features guided this precision. A mandibular flange on each side of the lower jaw helped brace the upper canines. Large infraorbital foramina, openings under the eye socket, held nerves for the whiskers, giving fine touch sense near the fangs. Big incisors at the front acted like pins to hold onto flesh, and the carnassial blades, back teeth, were long and sharpened for skinning. Dental wear patterns in fossils back this up. Microscopic grooves on the canines match quick slashing moves rather than bone crunching. Occasional canine tips show healed break marks, evidence that the cat took care not to break its killers. Smilodon's skull was not built for power alone, but for an accurate, one-shot kill. Smilodon's forelimbs were massive pillars of strength. The shoulders sat high with long scapula, shoulder blades, to support broad muscles. Humerine, upper arm bones, show thickened cortical walls. about 15% thicker than in similar-sized modern cats, indicating extra load-bearing. Powerful flexor and extensor muscles in the forearms let the cat pull down and pin heavy prey. Behind, the lumbar, lower back region was shortened, and the tail was very short. Unlike lions and tigers, Smilodon had no long tail for balance during a chase. A reduced spine meant a low center of gravity, perfect for a sudden ambush push and hold. The hindquarters were also strong, with thick femurs to brace powerful kicks and jumps. Bone structure shows a mix of strength and jumping skill. The long heel bone, calcaneus, and robust pelvic bones suggest Smilodon could launch its body upward to grip prey. Though built for power rather than speed, its limbs could still flex quickly for short bursts. Tracks attributed to Smilodon, called Smilodonicium, are 17.6 by 19.2 centimeters, larger than a Bengal tiger's, showing the cat's hefty feet. Compared to lions, Smilodon had shorter legs and a stockier frame. Tigers have longer hind legs for sprinting. Lions rely on team chases. Smilodon's build favored a strong first strike over distance pursuit. Muscle attachment scars on the bones are deeper than in modern cats, signifying bulkier muscles. Forelimb claws were fully retractable, but the wrist bones show less twist than in leaping cats. This means Smilodon's front paws stayed flat on the ground for a firm grip when it pinned prey, rather than rotating for a tree climb or tight turns. The thickened limb bones also hint that Smilodon risked more strain during a hunt, consistent with deep forest ambush tactics. Smilodon was an ambush hunter that thrived in forests, bush, or mixed woodland grass areas. Its short legs and stocky body made it ill-suited for long chases on open plains. Instead, it lay hidden in dense cover, waiting for large herbivores to wander close. When a bison, tapir, or young mammoth came within a few meters, Smilodon burst out in a quick lunge. The cat used its forelimbs as deadly tools. With claws out, it leaped forward, wrapping its strong front legs around the prey's neck or chest. This grip held the animal still. Powerful neck muscles then drove the head downward or forward, bringing the long canines into the target. Two main theories describe how Smilodon killed once it had hold. The classic canine shear bite idea suggests that the cat rotated its head and neck to slice the fangs through flesh in a scissor-like motion. The newer throat stab theory argues that Smilodon plunged its canines straight into the throat or belly, severing vital vessels. In either case, the prey would bleed out quickly. RoboCat experiments, robotic skulls, and neck models that mimic Smilodon's motion support the throat stab as more feasible. Tests on animal carcasses show that a deep throat wound is both quicker and safer for the cat, with less risk of bending a canine. Stab wounds on fossil bones and lack of wider tearing damage on the body match this method. Dental microwear adds more proof. Tiny, long scratches on the canines align with quick in and out thrusts rather than a slow slice. Some wear on the carnassials suggests the cat then used its back teeth to cut skin to access meat after the kill. Rare broken canine fossils also point to careful use. Smilodon avoided bone contact with its thin fangs. Large fossil track sites show multiple Smilodon prints together, hinting at group hunts or social feeding at kills. Even if the cat hunted alone, it may have shared kills. In the crowded tar pits of La Brea, dozens of Smilodon skeletons appear near trapped prey bones, suggesting they gathered at feeding sites. Stable isotope tests on Smilodon fatalis bones from Rancho La Brea show that about 50% of their diet was bison antiquus, the giant Ice Age bison. Another 25% came from camelops, an ancient camel, and the rest from forest dwellers like tapirs and deer. Occasional marks on sloth bones also point to ground sloths as part of their menu. When Smilodon moved into South America, its diet shifted. S-populator isotopes match bones of Macrauchenia, a llama-like hoofed animal, and Toxodon, a heavy grazer. They also fed on glyptodonts, armored mammals, ground sloths like catnecks, and even crocodiles such as Caiman laterostris. This mix shows they hunted in both open plains and thick woods. Smilodon shared its world with other big hunters. Dire wolves and American lions also ate bison and camels, and Homotherium, the scimitar-toothed cat, favored similar prey. But finer isotope work reveals small differences. Smilodon fatalis liked forest edge animals more, while dire wolves stuck to open-area prey. This niche split may have eased competition between these top predators. Coprolite, fossil dung studies add another layer. Some Smilodon populator droppings contain bits of armored sloth osteoderms and small limb bones. Dental microwear from Fatalis shows occasional bone crushing by the back teeth, though the long canines avoided heavy stress. This implies Smilodon sometimes scavenged carcasses or finished off kills left by other hunters. Evidence from La Brea suggests they both hunted and scavenged. Tar pit assemblages contain many Smilodon skeletons around trapped herbivores, which likely died trying to drink or eat from tar-soaked mud. After the prey died, multiple Smilodon may have fed together, snapping up flesh and gnawing on remaining bones. Their role as both hunters and opportunistic scavengers helped them exploit all available food. Overall, stable isotope data and fossil finds paint Smilodon as a flexible predator. In North America, it focused on bison and camels, but would take sloths or deer. In South America, it adapted to new hoofed giants and armored mammals. Competition with dire wolves, lions, and Homotherium drove it to refine its prey choices, while scavenging filled any gaps in its hunting success. Scientists still debate whether Smilodon hunted alone or in groups. One key study used playback experiments. Researchers played recorded distress calls of trapped herbivores at modern savanna sites. Social predators like lions responded strongly, while solitary cats did not. Applying this logic, Smilodon may have been drawn in by prey calls and stayed to feed with others, as its remains cluster around tar-trapped animals. At Rancho La Brea, dozens of Smilodon skeletons lie piled near herbivore bones. If each cat ran in from miles away, group hunting or shared feeding might explain the mass finds. Critics argue lighter animals get stuck more often, and smart hunters might avoid tar pits. Still, the sheer numbers of Smilodon bones, far more than herbivores, hint at social gathering at kills. Pathologies in some fossils point to group care. Several Smilodon fatalis show healed broken limbs or tooth injuries that would have limited hunting ability for months. A famous case of hip dysplasia in S. populator meant the cat could not walk well or hunt. Yet it survived to adulthood. Only aid from others, bringing food to an injured member, would explain such long-term survival. Modern big cats vary. Lions are social, tigers are solitary. Smilodon's brain size is smaller than many big cats, yet this does not strictly predict social behavior. Studies of living felids show no clear link between brain size and group living. Pathology patterns in Smilodon match those of pack hunters more than lone stalkers, suggesting that injured cats ate and healed within a group. On the other hand, bite marks on some Smilodon bones match those of fellow Smilodon, hinting at intraspecific fights over prey or mates. Such clashes occur in modern lion prides, too. If Smilodon lived in unisexual groups, males might battle for dominance, while females cooperated in raising and feeding young. Smilodon cubs grew uniquely. From 12 to 19 months, juveniles erupted their adult canines while still retaining baby milk sabers. For almost 11 months, these young cats had 2 sets of long teeth at once. A recent study suggests the old milk sabers supported the new ones, reducing bending stress on the growing adult fangs and letting cubs start small kills earlier. Adult saber teeth reached full length, about 28 centimeters in S. populator, by around 3 years of age. During this time, the cats developed strong neck and jaw muscles 8 months faster than modern lions. While baby teeth fell out between 23 and 30 months, adult canines grew at about 7 millimeters per month. This fast growth rate put Smilodon cubs on track for their deadly adult bite. Juvenile Smilodon fossils are rare at La Brea. This suggests young cats stayed hidden in dens or thick cover while their sabers matured, safe from predators and not risking damage to fragile teeth. They likely depended on their mother and pride members to bring food until they could hunt on their own. Parental care must have been strong. Cubs with incomplete canines could not wrestle large prey alone. Social groups could supply small bites of meat until adult fangs functioned. Evidence from healed injuries in subadults, plus the hip dysplasia case, points to adults sharing food with young or wounded cats. Compared to modern big cats, Smilodon's growth pattern had mixed traits. Tigers develop muscle and hunting skills early, but leave the family soon. Lions have prolonged care within a pride. Smilodon combined a fast start in muscle development with extended dental growth, implying long dependence on group members until full hunting ability. The La Brea tar pits in Los Angeles are famous for trapping Ice Age animals. Thick asphalt seeped up from underground, forming sticky mud pools near water and plants. Animals like mammoths, camels, and horses stepped in, got stuck, and died. Their distress calls drew predators. Many large cats, dire wolves, and short-faced bears followed the cries and also sank into the tar. This process, over 40,000 to 10,000 years ago, trapped a mix of prey and hunters in layers of sticky asphalt. Of all the bones pulled from La Brea, more than 166,000 belong to Smilodon fatalis. This single species is the most common large carnivore in the pits. Paleontologists have cataloged each bone, tooth, and fragment. The huge sample lets scientists track changes in Smilodon size, age ratios, and health over thousands of years. It also reveals patterns of how the cats attacked and fed on stuck prey. Bone breakage patterns at La Brea tell a clear story. Many limb bones of trapped prey are missing at the joints, likely torn off by feeding carnivores. Yet Smilodon bones themselves often show signs of chewing, weathering, and occasional breakage. These remains point to taphonomy, how bones decay and fossilize under asphalt. Bones buried quickly in tar avoid scavenger damage, but exposed bones crack under the sun and from trampling. Excavation layers capture these stages, giving a window into both life and post-mortem events. Further south in Peru, the Talara tar seeps played a similar role. Here, asphalt pools trapped young or inexperienced carnivores more than adults. Many Smilodon populator bones show surface weathering and disarticulation, suggesting slower burial and repeated trampling. Talara fossils include crushed skulls and broken limbs from thrashing animals, giving contrast to the quickly preserved bones at La Brea. Beyond these two sites, Smilodon fossils appear from Alberta, Canada, to Patagonia, Argentina. In Alberta's river gravels, teeth and jaw fragments hint at the northern reach of S. fatalis. In Uruguay and Chile, nearly complete S. populator skeletons appear in shelter caves and open-air sites. Each location adds detail. Climate, habitat, and local prey differ, but Smilodon remains a constant presence across the Americas until its final days. Smilodon's final fossils date to between 13,000 and 8,000 years ago. In California's La Brea pits, the youngest S. fatalis bones yield radiocarbon dates near 13,000 BP before present. In southern Chile, S. populator remains stretch into the early Holocene, about 8,200 BP. These dates place Smilodon's extinction firmly in the late Pleistocene animal die-off. Several factors likely combined to wipe out Smilodon. As the climate warmed after the last ice age, grasslands and forests shifted. Many large herbivores like giant bison, ground sloths, and mastodons declined or vanished. Smilodon, specialized for big prey, lost its main food sources. The loss of herd animals left fewer easy meals for these ambush hunters. At the same time, humans spread across the Americas. Early people hunted large mammals, perhaps competing directly with Smilodon for prey. Tools and coordinated hunts may have amplified pressure on herds. Smilodon might have scavenged human kills or avoided areas with people. Over time, shrinking prey and new competition created a tough environment for a cat built to take down megafauna. A long-held myth says that saber-toothed cats were clumsy failures compared to modern big cats. Critics argue that long canines broke easily and slowed feeding. Yet fossil evidence tells a different story. Smilodon thrived for over 2.5 million years, adapting to new lands and prey. Its precise killing bite and powerful forelimbs show specialization, not weakness. The repeated evolution of saber teeth in separate lineages further proves the success of this design. Today, Smilodon lives on in museum halls and popular culture. Museums worldwide display life-size mounts of S. fatalis and S. populator, drawing crowds to marvel at their curved canines. The La Brea Tar Pits Museum in Los Angeles offers a close look at dozens of Smilodon skeletons in their death pose. Films, books, and video games feature saber-toothed cats as symbols of raw power and ancient mystery. Smilodon combined brute strength with surgical precision in a way no modern cat can match. Its fossils speak to a world of tar traps, shifting climates, and changing prey. As a star of paleontology and a fixture in our imaginations, Smilodon reminds us how easy it is to lose even the fiercest hunter. In facing today's challenges, habitat loss, climate shifts, and vanishing species, what lessons can we draw from the fate of this great Ice Age cat?